Credits to roll here on the video. So. All right, now I can go. All right, good morning, everybody. I hope you all are enjoying the warm, sunny weather here in Arizona this time of year. Depending on where you're coming from, you're missing some miserable weather on the East Coast, apparently. So, today I want to first introduce myself. My name is Jim Schwiegerling. I am a professor here in the department. I teach. Currently teaching undergraduate geometrical optics and optical testing, so how to make and verify optical surfaces. And today I'm going to talk to you about optical engineering, not just stuff that is going on here, but stuff just in general to give you kind of an overview of what optical engineers do and some of the projects that they're involved in to hopefully get you excited. I know it's early in the morning, so hopefully the first cup of coffee is kicking in now, but feel free to ask questions as we go through here and stuff. And so my goal here is just to provide you with some information and get you enthused about optics. So optics, as we know, is a branch of physics that deals with light. And I put light in quotes here, and its properties and interactions with matter. So the reason I put light in quotes here is because light technically is the stuff that we can see. So the visible wavelengths from red to violets and stuff like that. But in actuality, in optics, we really deal with a much broader portion of the spectrum. So we really go from kind of the extreme ultraviolet all the way to the long wave infrared. And that's mainly because at those wavelengths we can find materials that do things like focus that energy and make images with it and that kind of stuff. And so pretty much it's all the same stuff. It's just a matter of the wavelength there. And I'm sure in your physics classes you've all come across having some sort of thin lens here, object over there, and it forms an image, and you can figure out what the magnification is. And so this is kind of the basic concept of imaging and stuff like that. But optics and optical engineering is a whole lot more than what you get here. And so I want to just kind of show you some stuff that goes on. So first off, optical engineers. This is kind of engineering is kind of a subgroup of the field of optics, and it really is an applied field. So you're trying to design and build practical things that do something useful. So your cell phone, I don't know, it's not so useful anymore because people hardly use it for phone calls anymore, right? And but there's a whole bunch of optics in here. There's the camera that's in here. There's the display that creates things. The signal goes to a cell tower somewhere that's hooked into fiber optics to transmit your data, your text messages, and your Twitter feeds all over the world and that kind of stuff. And so there's optics everywhere, basically packaged into this device. So some of the things that engineers are concerned with are, is it physically possible? You want to use the available technology. Typically, we're not doing sort of cutting edge, fundamental research, that kind of stuff. You're taking the stuff that used to be fundamental research and you're trying to find practical applications to it. Using available materials, and you're always worried about costs because you don't want your cell phone to cost $10,000. You want it to cost, well, $500 or $1,000 for your iPhone X, but that's still a little much from my perspective. Engineers need to be familiar with all sorts of optical components, so mainly optical sources, so different sources, obviously, sun, lasers, LEDs are a big one now. Optical components like lenses, prisms, fibers, those types of things. So it's going to take light from the source and it's going to do something with it. And then detectors. So you guys may be a little young, but this is a what's called film. It used to go into cameras and stuff. It used to be a very popular detector, but most things these days are either CCD or CMOS type digital sensors, and you all have sort of a built-in optical detector with your the retina of your eye. And so basically you're kind of mixing and matching these various components here and trying to do something new with that. Optical engineers are not, and this is a very common misperception, they're not optometrists and they're not ophthalmologists. Okay, so optometrists basically prescribes glasses, contact lenses, so they will measure your eyes, find out what's wrong with them, and then prescribe a suitable optical correction to fix those. Ophthalmologists are basically surgeons who will diagnose disease and possibly do either drug or surgical intervention to fix those diseases. So while we're not either of those, can certainly do things to aid optometrists or an ophthalmologist in their efforts. So optical engineer may design something like this. This is called a phoropter. This is the device that the doctor puts in front of your eyes and has a whole bunch of lenses that they flip in and out and stuff like that to try to figure out what your prescription is. So, and it's a fairly old, fairly clunky device for doing that. So this is just an example of a system that we built in my lab that tries to automate this whole system, and we run the movie here. Sorry, I have some volume here too. Maybe not. All right. So what we use are these deformable lenses, and so this is a fluid-filled chamber, and there's a PDMS polymer surface here, and as we pump fluid into here, it deforms the shape of that surface and changes its power. And we have a stack of 3 of these in there. So one of them has a circular aperture, and what it does is it corrects for your spherical power. And then we have 2 of them that have this rectangular aperture. And what happens with the rectangular aperture is as that surface deforms more in one direction than it does in the other direction. And so it can correct for astigmatism. And we've stacked 2 of them, and basically you can get astigmatism oriented in any direction with this stack of 3. So instead of having these wheels of lenses that we flip in now, we can just have this stack that's in front of the eyes, and it's it can automatically change the system. And let me just go back to the beginning here. So the system here, the 2 eyes go down here, and over here is a sensor that automatically measures the error in the eye, and it feeds back into the pumps, and then the pumps pump the fluid in and out of the lenses. So basically by sitting in front of this system, it automatically measures your eyes and then adjusts to compensate for that error so that you can look at the eye chart across the room and it suddenly becomes clear. So no more, is this one better or is this one better? Those of you who have glasses and contacts know exactly what I'm talking about with that. So, some other things. One of the big questions with these fluidic lenses is, doesn't gravity distort the shape of this lens and affect its performance? So we decided to check this out. And the way we check this out is on the thing affectionately known as the Vomit Comet. And so this is an airplane that will go up, and it sort of does this type of thing for several hours. And when you're going up this way, you are pulling more G's than, and so you're simulating high gravity. And then when you go down, you are basically getting low gravity types of situations. And so it alternates back and forth between low gravity and high gravity. And so here are a couple of my students, and so they built a system to measure these fluidic lenses in these low G conditions. And play this one. And so in here we have what's called a Shack-Hartman Wavefront sensor. It's a device for testing the properties of the lens and one of these lenses, and it just cycles through the lens. And as they go into the low G case here, they run their experiments. This guy on the left here doesn't look like he's feeling too good, so hence the name for the plane. So basically what we found was that there's so little liquid in these things that the weight is so small that the gravitational effects are negligible. So they actually do perform very, very well. All right, so as I said, light, or technically electromagnetic waves, we're dealing with everything really from ultraviolet and all the way up to sort of long wave infrared. We're really looking at these types of things. Ultraviolet has a lot of interest in things for like printing, computer circuits, and other types of things. And infrared has a lot of applications in the military applications. So in the visible wavelengths, we're typically worried about things like imaging. So you may design a camera lens, and notice here that these lenses are a lot more complicated than that single lens that I showed at the beginning, where you have some object and some image, and you find the relationship here. So typical camera lens may have 6, 8, 10, 12 lenses in there. And what you're trying to do is improve the image quality that's formed by that lens. A single lens actually will form an image, but the image will be distorted, blurry at the edges. The colors won't all focus at the same place. So as you add more components, you can fix those types of things. And so typically you have a much more sophisticated type of design in order to give you high quality design. So again, your cell phone, these days most modern cell phones will have 5, 6, 7 elements in here, and of course they're all only a couple millimeters in diameter in order to make it fit into the package here. But the quality of these, I was just on a trip up to Utah over Thanksgiving, and I had my big bulky digital SLR out one day. I'm like, why am I carrying this around? When I take pictures with this, I get about the same image quality. So I just left it back at the hotel and just took pictures with this camera. This is an example of a zoom lens. So not only do we have these multiple elements, but now we can start moving the elements relative to one another in order to do things like change the field of view. So I can go from taking a picture of all of you to focusing in on a single person. Here at the University of Arizona, we do a lot of optics development. And I think you're getting a talk tomorrow about a couple of these things. But basically, any of the pictures that you have seen from Mars, basically were taken with cameras that were built here at the University of Arizona. In fact, across the mall here, there's a little fenced-off area that's a simulated Mars environment. So it's a bunch of red gravel and rocks and stuff like that they can test things. So this is just a picture of the surface of Mars from what's called the high-rise camera. So this is a spacecraft that is orbiting Mars, and it's just taking photographs of the surface. And again, the cameras were built here. we've also been involved in what's OSIRIS-REx, which is another spacecraft that was launched about a year ago, and I think it's about halfway to its target. So this craft is going out to an asteroid, is going to pick up a sample of the asteroid, and it's going to send that sample back to Earth. And so we'll actually get a chunk of this asteroid from there. And I think there's a talk on this tomorrow. But as you can imagine, there's a lot of optics that go into here. So you want to be able to visualize the surface as you're coming in close to it, and basically see where you're going, and be able to get something onto the surface is fairly challenging. Some other types of cameras. So we distort imaging a little bit. So this is something called a Plenoptic camera, and so what it does is it puts a sort of series of tiny lenslets over the image plane, and instead of recording the image directly, what it does is sort of records a whole bunch of little tiny images of the scene, and there's some overlap between each of them. And so if you take two of these, you can kind of think of this as a stereo camera, right? So two of them, you can find features in each image that tells you what's the distance of the target. But now you have 1 million of these, or at least a couple 100,000, and so each of those pairs are acting like a stereo camera. And so from that you can get depth for all different portions of the scene, and you can do things like refocus the picture afterwards. You can change the depth of field of the picture afterwards. So I can go from being focused on something up close here to something far away, and sort of the modern version of this is starting to be used in things like movies. So you can do things where you can film a scene, and then you can insert objects between two things that are actually in the scene. And so you can do this all in post-processing and stuff like that. If we go away from the visible now and we go into the infrared, we have some different properties here. So you actually also have an infrared detector built in. So our eyes are good for visible wavelengths, but your skin is basically an infrared detector. And so what you are feeling when you feel the warm sunlight outside is basically the long wave infrared radiation is being absorbed by your skin, and you're detecting it as heat. So you're not really forming an image. But we can build a camera system that can record these wavelengths as well, and basically give you a temperature map of the scene. And so this one, for example, is just somebody taking their finger on a surface and writing out the word friction on there, and the temperature change just coming from rubbing your finger on that surface is enough to be picked up by the camera here. Empty chair with somebody who had sat in it, their body temperature has heated up the material and changed it. So handprint on here, and a foot being scraped on the ground here. So so this has all sorts of applications. So things that may be invisible at the visible wavelengths would be readily apparent in the infrared. So obviously there's military applications for this, or things like you can detect things behind walls in your house and stuff like that. So like leaky pipes and that type of thing. And nowadays, in the long wave, the price of the sensors has come down dramatically. So for $200, you can get a infrared camera that plugs into your phone, and you can take pictures like this with that type of thing. So also in the infrared, so you're getting a talk tomorrow by Charlie Falco, and he does a lot of work with art And so in the visible wavelengths, when we look at this painting here, it looks pretty much intact. But if we go into the infrared and look at it, you can see a lot of areas here where the paint is delaminating from the canvas. And so this is a way to help art historians understand where damage is and do some things to try to repair and preserve these types of paintings. We can also go to the short wavelengths, so the ultraviolet type wavelengths. And so on the picture here on the left is the visible wavelengths of a person putting on sunscreen. Okay? And if we go into the infrared, it looks like she's smearing mud all over her face. So, but this is a good thing, right? This is exactly what you want. You know, sunscreen is meant to block ultraviolet wavelengths. And so the fact that it appears dark in the ultraviolet means that it's absorbing all that ultraviolet light as it should be, and it's not getting penetrating into your skin. Another example of ultraviolet technology is the excimer laser. And excimer laser is a ultraviolet laser that's used for LASIK surgery. Okay, anybody here had LASIK? No? Okay. Well, I'll show you the surgery, and then you can decide afterwards if you if you want to do it. But the laser here was originally developed at the Watson Research Labs, and the primary researcher was enjoying Thanksgiving dinner, and it struck him that his brand new excimer laser would be highly useful for vaporizing tissue. Okay, and so he brought the turkey carcass into work on Monday morning following Thanksgiving and ran some experiments with it. And so if you can see these types of things here, this is with a argon laser. So it's a green laser, high-powered laser. And basically what it's doing is it's burning the material. It's charring the material. And all this stuff that you're seeing here is damage that's occurring to the tissue because of the absorption of that energy and the burning effect. Next to it, these channels here are the excimer laser. So at this wavelength, what happens is that the proteins that are in the form the tissue absorb the energy, and it breaks the molecular bonds. So they literally just kind of fall apart. And each pulse of this laser removes about 1/4 micron of material in depth. And so it gives you a very precise and smooth type of way of removing biological tissue without causing collateral damage to the tissue around it. And so this laser is used for LASIK surgery here. And let me run this here. And so LASIK is meant to correct for refractive error, so nearsightedness, myopia, hyperopia, astigmatism. We put in a speculum here for to keep the lids open. This is just a little ink pen marker to mark positions on the cornea here. So, oh, this is a great device. You're going to love this. All right. So this is called a microkeratome. It's basically a suction ring, and there's 2 tracks on the side here, and it kind of sucks onto the eyeball and holds it steady. And this is the other piece. This is a mechanical blade, oscillates back and forth, and it's going to shave across the eyeball here, and it's going to create a little flap in the surface of your cornea. It doesn't go all the way through the cornea. It goes about 1/3 of the way through the cornea. All right. So we'll see the flap here in a second. All right, so who's ready to get LASIK? So, all right, no? Wait for the surgeon here to catch up. All right, here comes the flap. Oh, God. So did you guys all enjoy breakfast this morning? Yeah, all right. So the purpose of doing this is that we're going to use the laser to sort of vaporize the tissue inside the cornea, and then we're going to put that flap back on, and the flap acts kind of like a protective layer after that. So get this all lined up. And the laser obviously is ultraviolet, so we won't be able to see it, but the corneal tissue actually fluoresces when it gets zapped by the ultraviolet, so you may be able to see like a faint purple splotch when they're actually zapping the cornea here. So now the laser is going to start, and it's going to pulse. Watch for the purple flashes in here any seconds. All right, so you should see a few flashes in the center here of this fluorescence, and so basically it's sort of opening up and vaporizing a disc of tissue off the surface, and it's changing the shape from something that looks like this. It's going to vaporize the tissue to take it down like that, and what that ultimately does is when you put the flap back down, it changes the shape of your cornea, and consequently the power, the focusing ability of it. All right, some more flashes here. And that's it. All right, so this person went from having worn glasses since they were a kid to they'll be able to pretty much sit up from this and see pretty well. And within a couple days, they'll probably, be spectacle free. Lay the flap back down, and you can kind of see the reason for the ink marks here is you want to line up the flap with the ink marks here to make sure you got it in the right position. There's no stitches, and this flap just kind of gets sucked back down onto the surface here, and it will stick. Okay. All right, so other technologies here. So we're all familiar with the barcode scanner here. So basically we're putting out beam of light, and it's scanning back and forth very quickly, and we're looking at the reflectance off the surface, and there's a detector in here that's looking for intensity variations and some sort of code that's encoded by those intensity variations. But we can do some more sophisticated things with that type of concept here. So we can do things like 3D laser scanning. So here you're projecting a line onto a surface and then looking at that surface from a different angle. And basically you can triangulate on, if you know where the source is and you know where the camera is, you can figure out where in space those two things must meet, and it gives you a 3D map of the surface. And so you can think about here, we're projecting a plane slicing through the surface, and this is defining the intersection of the plane with that complex surface. And by knowing these points, we can build up the surface, and then we can scan this across the surface to recreate the scene. So, and we can do not only little objects like this, but you can do big objects, and this is slightly different technology. So this is a sort of ladar, which is sort of laser radar, if you will. So it fires out light, looks for the bounce off a surface, coming back and measures the amount of time it takes to for that round trip travel. And so you can do things like the historical sites here. I saw this cool demo where they took a picture out the window across the parking lot and into another building, and you could actually see people inside the building walking around in their offices and stuff like that because they were sending signals back. And if you take 2 of those pictures and eliminate anything that's moving, you can do things like strip all the leaves off of a tree, because typically on a windy day the leaves are moving, but everything else is fairly static. And so when you do the difference between those two, you basically just get all the leaves, subtract that off the image, and you can now, instead of being blocked by foliage, you can actually see through the foliage. This type of technology is being used in autonomous vehicles a lot to understand what's going on around the vehicle. And so other cars, people, objects in the road, those types of things. And so if you've seen any autonomous vehicles, a lot of them have this sort of big monster thing on the roof, and it's basically this laser kind of spinning around and taking a map of the environment as it moves. Head-mounted displays are another big area right now. So virtual reality, augmented reality. One of the problems with them, though, is that the field of view is limited, and the thing is pretty bulky. So you're basically wearing this brick on the front of your face, and it's not particularly comfortable. So what if there was a way that we could get rid of that type of thing? So here is an example of a technology that can do that. So right now, these head-mounted displays, you have your eyeball and some lens, and then there's a little display here that's showing you the material. And the reason for that big bulk is you got to have enough separation between these two and this in the eye in order to form images that the eye can see. But what if we could take this lens and we put it on the eye? Okay, so this is a contact lens that goes on the eye, and then in the center here, this little tiny but super high power lens that lets you focus on something that's only about 16 millimeters in front of your eye. Okay? So if you are just walking around with this thing, you actually don't really notice this because there's light going in the periphery of the lens here, and so you can walk around just fine with these lenses and see just fine with them. But if you hold something up super close like this, it will be in focus. Okay? So here's another shot of the same lens here. And so what you can do with this now is you can make a pair of glasses, and you can make the inside surface of these glasses the display. So instead of having this brick on the front of your face, you just have a pair of glasses, and that little tiny lens in the center of the contact lets you focus on the inside surface of your glasses. Okay? And so now you can project the scenes that you want to see. Field of view becomes very, very wide because you've moved the lens closer to the eye, and it looks like a funky pair of glasses instead of a big monster headset. Now we can take the same concept too, and I'm going to shut the light off for a minute here. Maybe. So, kind of hard to see on the screen here, but there's this big bump on the surface here again. And so, one of the other things is if you go underwater, basically you have this interface between the water and the cornea, and you lose all the power, the focusing power of the cornea, because there's fairly small differences between the material of the cornea and the material of the water. So we can't see. Things are blurry underwater. But what if we put on this contact lens now, has this huge power lens on the front again. And so what this does is it allows you to see underwater. So you come out of the water and you basically use the periphery of the lens and you can see just fine. You go underwater, you use the center of the lens and see just fine clearly. And so we built some of these and did some underwater eye testing. So this person reading an eye chart underwater. And so basically they were able to get really good vision with these lenses underwater with no, there's no mask or anything that's on here. Okay. Go back to, magic, yes. These are something called scleral contact lenses, so they're very, very big. They actually go way out onto the white part of your eye, and your lid is basically retaining them in the eye. So, any other questions? All right. Navy's been interested in these types of things for obvious reasons. I had a student who was a water polo enthusiast, and she was very interested in it because not having to wear goggles during the games was a big advantage. Now let's talk a little bit about some other things here. So this is kind of a cool thing called Schlieren imaging, and so this is a technique of being able to visualize things that are normally invisible. Oop. Go back here. Why are you not playing? All right. Let me. I'm going to do the old-fashioned. Let's do it this way. Oh, hang on. All right, so Schlieren, like I said, is a technique for being able to see the invisible. So this is a razor blade and a camera lens, and next to it is a source. And then across the room is this big mirror. And so you can put things in front of this mirror and actually see distortions in this case in the atmosphere here. So the heat from the candle flame here is changing the index of refraction of the air around it. And the setup is changing the phase information that's usually invisible to us into contrast so that we can perceive it. There's a hairdryer. This is helium being put into a glass. Helium is lighter than air. All right. So now as you tip the glass, the helium will pour out, but it's pouring up because it's lighter than air. Sulfur hexafluoride is another gas, but it's actually heavier than air. So normally we can't see anything, just pouring nothing into a glass. Oh, but now the glass is overflowing. And now if you pour it, you're pouring the gas out. Emptying it out. good to the last drop. All right, I don't think we want that. So, all right. So, another type of technology here is we try to intervene with cataracts, and cataract is a opacification of the lens that lies behind the iris in the eye, and so it usually occurs because of UV exposure. So out here in sunny Arizona, you're constantly getting UV exposure. You get a lifetime of that, and it accumulates, and you get these defects. So think about taking a piece of plexiglass and leaving it in your backyard in the sun, and it starts to yellow with age. Same type of thing is happening with your lens. Typically, in the Western world, we'll get something like this, and the doctor will go, "Oh, you need cataract surgery, and we need to take out that lens, and we'll replace it with an artificial lens." A lot of other places in the world don't have the same access to healthcare that we do, and the cataract may look like this. So the entire lens now is opaque, and this person is blind because no light can actually get into the eye, even though it's functioning just fine otherwise. So roughly 20 million people in the world are blind because of this situation on the right, and it's actually very easy to fix these days. And so we're fortunate to have that ability. A little history about cataract surgery in the old days. What they used to do is just take that lens out, and what that does is it lets light back into the eye. The problem is you've lost a bunch of the focusing power of the eye, and so you have to replace that with these very heavy-duty spectacle lenses. And so if any of you know what your prescription is, these are something like a 20 diopter prescription. So most people that are wearing glasses will have like a 3 diopter type prescription. And so that was the original thing, is just pull out that opaque lens, and we'll just put some glasses on in order for the person to see. Back in the 40s, there is a gentleman named Harold Ridley. So he worked as a ophthalmologist and treated Royal Air Force pilots. And what he noticed was that there was these fighter pilots in World War II, and the canopy on the airplane here was made of a new type of material called perspex. We call it plexiglass or acrylic. Okay? And what he noticed was that occasionally some bullets or whatever would go through the canopy here, and shards of this plastic would get embedded into the eye. And he noticed that the eye didn't respond. Okay, so if you get a splinter in your skin, your body sort of encapsulates that splinter, builds a big hard area around it, slowly works it to the surface and tries to get rid of it. So typically if you put a foreign body into your body notices it, and it tries to isolate it and get rid of it. Okay? In this case, that wasn't happening. And so Ridley came up with this great idea. It's like, hey, why don't we make a lens out of this material? We can stick it in the eye after cataract surgery so that the person can see again. And he told some of his ophthalmology buddies about it, and they thought he was crazy. Why would you want to put a fake lens in somebody's eye when you can give them a perfectly good pair of spectacle lenses and they can see? Well, he had to sort of do these surgeries in secret in order to test out his theories. And so the first surgery he did, he implanted a lens, and it took the person, typically when you pull the lens out of the eye, person's super, super farsighted. Put it in the lens, and the person became super, super nearsighted. So he was able to demonstrate that that he could change the focus of the eye by putting this artificial lens in. He just changed it a bit too much, made him super, super nearsighted now. But the concept was sound. Second time around, did the same thing, same result, super, super nearsighted. It was then that they realized that they had no idea how to make this lens, so they just kind of made it the same shape and size as the lens that's already in the eye. But the refractive index of the plexiglass is higher than the refractive index of the lens in the eye, so it has more focusing power, and so that was what's causing this this extreme nearsightedness. So by the third time, they had figured that out, modified the shape of the lens, and they were able to get the person pretty close to being able to function without glasses. Told people about it, and they laughed at him and threatened to take away his medical license and and those types of things. And so it didn't catch on for many, many years. So it was really 20 years after this that it finally started catching on in the United States. And then nowadays this is just standard procedure. So if you talk about cataract surgery is taking the lens out, putting the artificial lens in. And so I have a video of this one too. And if you notice, there's a kind of a reoccurring theme here. There's a lot of eye stuff in here, and I do that because I do a lot of eye stuff. And so that's kind of my field. But I think we'll skip the audio on this one. It's kind of boring. But hopefully we'll jump to the surgery in a second here. A lot of times what they'll do is they'll do just a brief general, and they'll give you a shot behind your eye to basically kill any pain, and then they bring you out. A lot of people getting cataract surgery, 70s and 80s and stuff like that, you don't like to do general anesthesia on them if possible. So he made a small incision into the cornea here, and now is squirting in kind of this viscous goo, keeps your cornea inflated while surgery is being performed. And then the lens inside the eye is inside an elastic bag, and so here he's peeling off the front surface of this bag so that you can get to the lens that's inside. No, so this is behind the cornea. So this is kind of, I'll do the side view here. Cornea is like this. This is your iris, and then back here is the lens, and it's in kind of a bag, and so it's going in through here and then peeling off this part of the bag. So here just kind of squirting in some water to inflate the bag and separate it from the lens inside. Kind of rotating the lens around there, trying to loosen it up. So, and this one's called a phacoemulsifier. And so this is a probe, and the end of it is hollow, and it vibrates high frequency. And there's vacuum that's sucking on this. And so you touch the probe to the lens, and the vibration shatters the lens into pieces, and then those pieces get sucked out of the eye, and at the same time it's injecting fluid into the eye to try to keep the volume the same through the whole thing. And so as we go through here, you can kind of see bits and pieces being sucked out. I'm going to zoom forward here a little bit if I can. Oop, sorry. I guess I didn't. I don't know why it's not giving me. I don't know why it won't let me zoom through. All right. See, problem with technology. All right. Well, I'll let this play. All right. See if I can do it this way. There we go. All right, so I'll zoom ahead here. Oh, jeez. All right, so I was just basically going through and sucking out pieces of this lens. So it's breaking it up into bits, and going to take this lens out. And then what we'll do is insert a artificial lens in here. It'll look something like that. And then this bag actually kind of shrink wraps around the lens and holds it into place. Oh, that's good. Good segue here. So let's zoom ahead here a little bit. So this is just a modified probe. It has a little bendy end. Just reach behind the iris, get any little bits of things that are hiding back there. All right, and so let me back up a little bit. More. All right, so now they're going to take this artificial lens, they're going to roll it up like a burrito. All right, and they stick it in this little injector, and they kind of jam it into this hole. This hole's only a couple millimeters wide. And then as you inject it in there, it's going to come out and it's going to unroll, go from a burrito to a quesadilla. Yeah. I'm sorry? Yeah, so a lot of them are acrylic based, but they're usually modified so that they're flexible for exactly this reason, so that you can roll them up. So they're either silicone or acrylic are the base materials. You can see this little arm on the lens here, and this is basically so it can just kind of wedge up into the space here and hold the lens in place and keep it centered within the iris here. It's plastic. It's a polymer, yeah. and you know, just some alignment here and that kind of stuff. This is outpatient procedure. The whole video here takes about 20 minutes or so. And so you can take somebody who's completely blind and 20 minutes later restore their vision, and they can pretty much sit up from this and see pretty well as well. And again, usually after a couple days you're where you're at. Yeah.
It's like, can they shape the lens so they don't even need like normal corrective glasses anymore?
Yep, absolutely. So and that's you know, some of the stuff that we work on are things like, okay, I know what the eye is with the lens in there. I got to guess what the properties of the eye is when I take the lens out, and what lens I should stick in there, and where does it sit in the eye. So those types of things. Another thing that you may sort of deduce from here is the way that we change our focus is that the shape of the lens here changes. So when you're focusing on something close, the muscles kind of contract down, and this lens becomes fatter and lets you focus on things up close. And when it's relaxed, you're ideally focused off at the distance. When we put this artificial lens in there, that doesn't happen anymore. This is just one lens fixed, so you're frozen at some distance of your focus. And so one of the things that we work on are called diffractive lenses, where we put a structure on the front surface of this implant and allow light to be split into multiple foci. And so we have a lens that is a trifocal, so it has one focus for distance, one for computer, and one for about right here where you read. Okay? And it's being implanted in Europe right now. So, and so it solves this problem, being able to not being able to focus at different distances. So there's only a couple of us in here who have problems focusing at different distances, and so as you get older, you naturally lose this ability for the lens to flex, and so that type of lens may actually be done in a perfectly clear lens, but that one that can't focus anymore. All right, so that's all I have. We have a couple minutes here, and so I can answer some more questions if you like. Why don't you go to the next slide? There we go. And there's Carl, weightless Carl. Yeah.
Question more about like bio question, but when you said like you get older and you can't focus anymore.
Yep.
Is that more the lens won't bend anymore, or the muscles aren't strong enough to bend it?
It's the lens has become stiffer and bigger with age, and so there are a bunch of people working on lenses that actually do change shape, and that's probably the next generation of lenses. So hopefully by the time you need this stuff, that will be the natural, natural one. So yep.
When they're corrected for nearsighted or farsighted, because if you take off like part of the layer
of the cornea, what's changing? So what's happening typically with, let's say, somebody who's nearsighted is that the light's coming through these two lenses and focusing, but the back of your eyeball's back here. And so you want it to focus here, but instead it's focused here. And so what the laser surgery is basically doing is it's changing the shape of this front surface, making it flatter. And what that has the effect to do is that the eye can't focus down as quickly, and so it pushes that image back towards the retina. Yeah, so for farsightedness, typically what you're doing is, if this is the original cornea, you're creating something that sort of looks like that. So you're vaporizing this tissue out here, and you're making that surface more curved than it originally was. Yep. Yeah.
Do they focus after that if their muscles can't?
They don't. So so But I mean, the lens. Ideally, you pick the lens, and they're frozen at distance, and so they can drive and go outside and see just fine. But if they want to read something, everything's blurry, so they put on reading glasses. And so the purpose behind the diffractive lenses that we do is that you can see at both distances, and see well at both distances, and not need the glasses. So, yeah.
Gases. What's that mirror made out of? It's reflecting the visible, and then also the.
It's just a regular silver mirror. Yep. Yep. So what's happening in that case is there's a light source here, and then a camera, and then there's a little razor blade in front of the camera that's kind of halfway across here, and then the mirror is curved, but it's just a conventional mirror, and it tends to focus right at the razor blade here. And so if you put in some object here that distorts the rays coming off this mirror, some of them may go over here and hit the razor blade and not make it in, and so that would appear dark, and then other ones will still pass by the razor blade here and appear light, and so that's what gives you the contrast between the different refractive indices in the scene there. Yep. Okay. Okay, so undergrad or graduate? I was assuming we were talking about graduate here, but I mean, really, we have both. So right now we have, for undergraduate, we have 120-ish students. They usually start their sophomore year. All engineering students here at the U of A are required to take the same classes freshman year, so they take physics and chemistry and intro to engineering and math and that stuff. And then in their sophomore year, they decide which engineering branch they want to go into, and so a subset of them pick optics. A lot of those students, I would say about 3/4 of them go to industry, and about 1/4 of them will stay on and typically do a master's degree here. And all of them have multiple offers, so they're having to pick and choose which place they're going to work. For graduate students, we have 300 graduate students here, so there's about 150 master's students and 150 PhD students. So we typically take close to 30 PhD students every year. Typically, it's about a 5-year process, 2 years mainly of classes, learning how to do research in the lab, getting tied in with a professor, and then 3 more years of kind of doing your research, writing it up, and defending that type of thing. Same thing with the graduate students, is that they all are getting multiple offers. Apple and Oculus and Microsoft are banging on our door saying, give us more. We need more people. They're super high demand in those areas for the head-mounted displays especially, but also all of them are doing sort of self-driving cars and camera systems and that kind of stuff. And so, but there's also national labs, aerospace type of stuff. So a lot of people doing imaging with satellite imaging, airborne type imaging, remote sensing. So looking at the Earth and trying to gather information about the health of the Amazon rainforest, water temperatures, things like that. I'm trying to think where some of my students have gone. So, making diagnostic equipment for eye surgery. That's where a lot of my students end up, and so they're building the systems that they're building that laser system, or they're building the stuff that measures your measure your eye, that kind of stuff. So. Other questions? All right, I think we have a break here. So I'll be around, so if you have any questions, feel free to come up and ask me. I'm happy to answer. Thanks.
Good morning, everyone. My name is Jose Sasian, and I am delighted to see you here. I hope you are having a great time. Are you? Awesome. What do I do? At some point in life, you will ask yourself, well, what do I do in life? Well, but you are very young and you are defining what you want to do in life. But in my case, I am more kind of older and I already have defined what I want to do in life. And one of the activities I love, one of the activities that I have a passion for is lens design. And in the next 20 minutes or so, I want to convey a little bit of how exciting is this for me. How lens design, the activity of lens design, dealing with optical systems, designing optical systems is. One of the things I tell my students in Optics, Opti 517, which is Introduction to Lens Design, is to ask, some of them would wonder if they are okay taking this class. And I tell them, you are making no mistake in being here. Because you have to have, as an optical engineer, and I'm assuming you are in love with optics, and whether you are in the photonics, the quantum, the imaging, or the optical engineering fields, you will have to have some idea about how to put together a lens system for a prototype, for an experiment, for a system. Developing the skill of lens design, it's very handy, and you will see why. What is lens design? Let me grab a pointer because I like to work with pointers. Right here. Well, lens design deals with designing the optical components such as lenses, prisms, that will go into a system such as consumer optics. This is a pair of binoculars. I've been designing some of these systems where the criterion for success has three components: cost, packaging, and power efficiency. You can come up with many different ideas, many different designs, but the ones that win are the ones that are going to meet the specifications. The specifications are an important thing in any optical systems to start the design. In terms of optical specifications, we can talk about the field of view, the F number, for example, the transmission. But given the specifications, the products that will win are the ones that have the least cost, the best packaging, and the best power efficiency. Here, it's another example that you may be a little bit familiar, which is the lens for a cell phone. Modern cell phones have lenses that have like 5 or 6 elements. The field of view, it's about plus or minus 38 degrees. How do you put together a lens like this? Well, that's the subject of lens design. The standard SLR camera also has a lens. In this example, we have a double Gauss lens, and someone has to design those lenses. There are a number of applications, needs for lens design, like camera lenses, telescopes, microscopes, lasers, communication systems, consumer optics, optical instrumentation, many, many systems. One system that I worked after I graduated was a photonic switching system where rather than using wires to convey optical signals, we want to use beams of light to convey phone calls from the input phones to the output phones. And what we did was an experiment, a prototype, having 6 stages where we would input the signals through a fiber bundle, input them into a symmetrical seed device where the information is processed. We will read that information with a laser and transfer it to the next stage a number of times in such a way that we would establish the interconnection so that one would be able to call from your phone to a friend's phone. That was a dream many years ago, and today, to some extent, it is implemented to be able to communicate so many phones efficiently. Here at the College of Optical Sciences, and I am going to expand my scope, not only lens design, but I'm going to talk about optical design in general, because I want you to be aware that here at the college we offer a very comprehensive curriculum in optical design. Here are some of the courses that faculty is offering. Professor Grevenkamp teaches the optical design and instrumentation course. I teach the introductory lens design course, also a course in aberrations. Professor John Koschel teaches the illumination engineering, which is a very important course. Ross Schiffman teaches the polarization in optical design. Professor Lyon teaches advanced optical design, and Professor Takashima teaches photonics in lens design. This is really a very comprehensive curriculum, and probably the most comprehensive in the world. So coming here, you will have access to all of these courses and to really develop an expertise in optical design. I have over here the list of industrial affiliates of the college. There are many, many companies like Microsoft, Apple, Nikon, Canon. You can read them. And why do I bring up this list? And the reason is that they provide support for students and job opportunities for all of you. They really are investing in the students who come to the college, so that when you are finishing, if you come, you already have maybe 1, 2, or 3 job offers. That's not uncommon. And many of these employers really are looking for students who have skills in optical engineering, students who know how to do lens design, illumination design, optomechanics. So it is really very exciting because once you come to the college, provided that you are present in your courses, you pretty much have guaranteed a wonderful life and an interesting life doing a wonderful career. It's true. It's true because I have gone through it, okay? And many others too. Now, how do you do lens design or optical design? When you graduate, your job is not going to be done with pencil and paper. You will be handling programs, software, maybe finite element analysis programs, MATLAB, optical design software, lens design software, to do what you have to do. And a classical way to get into software, because that's something you really need to get into, is through lens design, where you learn to model basic optical structures and do predictions of how the image will look like or how light is propagating. So software is very important. It will be very important in your life, optical design software. And in terms of lens design, Some of the software we use are Code 5, Oslo, Zemax, Synopsys, Optical. Let me just give you a little bit of a sense about how this software looks like. I have over here Code 5, okay, and it has a doublet lens. And you have, I mean, these are very, very powerful programs, and you can do quite complex analysis and modeling of optical systems. But I'm just showing you a very simple doublet. Here we have the specifications where the radio of curvature of these surfaces, the glass. I can do plot the optical path difference to get an idea of the quality of the image. I have also over here Zemax, which is another lens design software, analyzing a double Gauss lens. But before I go further, this is not a single way, a one-way street. It's supposed to be a two-way street, so you need to ask me questions. Yes? Both are wonderful.
Can you do like Gaussian optics?
Yes, you can do both Gaussian optics. They have physical optics propagation. Okay? So now let me tell you about a few projects I have been involved, and one of them is the Large Synoptic Survey Telescope, which it's a very large telescope, and it's going to be installed in Chile. The optical design consists of a primary mirror having an aperture of 8.4 meters. The F number of the primary is F1.1A, which is very fast. And then it has a secondary mirror, and then it has a tertiary mirror, and then a system of 3 lenses which are expanded here to produce a very, very, very good image over a diameter of 600 millimeters, okay? It's about this size, the image size. The size of the image on your cell phone is about maybe 6 millimeters, but this is about 100 times larger. It's a very large telescope. The primary mirror is from that wall to that wall, approximately. And just imagine the spot. These spots are in the order of 5 micrometers on the side. And if you do the computation of how many spots fill this 600 millimeters diameter, it's about 1 times 10 to the 12, 1 terabit of information. It's a huge amount of information. But astronomers would like to, it's not completed the telescope. The mirrors have been done at the Mirror Lab here, which you will be visiting, I think, on Saturday or Sunday. It's an impressive place. Astronomers would like to be able to do some testing. So we were asked to propose a simulator for this telescope. And the specifications given is that the F number has to be 1.23, same as the large telescope. The performance has to be diffraction limited. These are the specifications for the simulator. The image field has to be 60 millimeters, 110. And the size needs to be about maybe 25 inches long by about 12 inches in diameter, something that you can put on a tabletop. Those were the specifications we were given, and we submitted a bid. We have a concept, and we won it. And so we have to do the design, and I want to show you the design here. we won the bid because we were able to do it in about this size. Keep in mind that the telescope is 8.4 meters in diameter, and having this in this size means that the cost and practicality would be very high. The cost very low, the practicality very high. And the main concept to being able to do the design is that we have this beam splitter here, light from the object, in this case a plate with lots of pinholes simulating the stars, will come through the beam splitter and then to this spherical mirror. Light will be reflected back, and there is a coating here to send the light back over here. So this folded configuration that is throwing away 75% of the light, that was the only penalty, but that was not a problem because they have lasers here, a lot of light. So we could throw away lots of light. Then light would come over here, get 25%, and get a pretty good image quality over the 60 millimeters that was required. So this is one example of the design task that we had. And it was very exciting because before we came up with these solutions, all other solutions were very large. But because we decided that if we could throw away, and this was a key question we asked, can we throw away light? And the sponsor said yes. And then this came up very nicely. Any questions about this? It's very easy to remember. It's F1.234. You couldn't forget it. Well, the F number, what is it? In many camera lenses, like your cell phone, you have the lens here, and I'm going to represent it like so. This is the optical axis. Light would come like so from an object very high, very far, and it will focus, okay? And then if this is the focal length, and this is, say, the entrance pupil diameter, the F number, it's given by F divided by D. And the lower the F number, the brighter the image is going to be. The eye has an F number of about 2.8, and earlier phone lenses also have an F number of about 2.8. Now cell phone lenses are tending to an F2, so that you can take good photos under low level of illumination. Here it's a plot of the black line represents how tight the light it's in focus, and the color lines represent the different what are they? The different field points, I believe. It's just a measure of image quality, because you have to say how good the image is, and one measure is the encircled energy. Another project we have worked is in designing cell phone lenses. Cell phone lenses are produced not by the thousand, not by the million, but by the billion. So the yield, that is how many lenses will work out of a billion you produce, it's very important. And anything you can do to increase the yield by 0.0001% represents a lot of money. So you want to do everything you can to maximize yield. And one of the things we did was to come up with a new surface description that make the tolerances of these lenses wider in such a way that the lens was more resilient to errors. That's another project in lens design. One of my students presented this work at the International Optical Design Conference in Denver this year. So students participate, as you know, in writing papers and going to conferences, which is a very exciting activity. More questions? Yes.
Source of light, or is that the different wavelengths of light? And then
Okay. Here, we're assuming that the light is coming maybe from an object that is very far, which could be, for example, that chair, okay? And the center of the chair is sending light represented by the blue beam. And the corner of the chair is represented by this beam of light. And in between, we have different beams of light. So this is the field of view. And we want a tight image here, a tight spot, so that we get a sharp image. And the software has, lens design software has many ways to evaluate image quality. Yes? That's a nice question. Why SLR cameras don't use plastic? And plastic has a much larger coefficient of thermal expansion and is more sensitivity to humidity. So it's not as stable as glass. And that was a problem of the earlier cell phone lens manufacturers. They didn't believe that plastic would succeed. But because of the very small size, about 2 or 3 millimeters or 4 millimeters in diameter, they really succeed. At that size, plastic is as stable as glass. And they prove that, indeed, those lenses are pretty stable and perform very, very well. However, the lenses for cell phones, the industry, is now moving back to glass. And the reason is not stability. The reason is that they want to make the lens thinner and thinner and thinner. And because the index of refraction of plastic is to about 1.6 or so, there is a limit on how thin they can make the lenses, the overall lens. But using glass, having a higher index of refraction, they can decrease the thickness maybe by 0.5 millimeter, maybe, which is substantial. And so that's the reason why some companies are considering getting back into glass for maybe the first element. Here is a blowout of the different components of a cell phone lens. You have over here the 5 lenses. You have the sensor over here, and you have the optomechanics holding the lens, and the voice call moving the lens for focusing. Lens design uses optomechanics. We have to mount the lenses, and we have to have an idea of what's good, what's not good, and so forth. There are many jobs for people who understand optomechanics. And the last project that I like to share with you, it's simulating the arc source of the emission of an arc source. How do you do this? We have over here some representation of the luminance distribution of an arc source. And you would like to be able to simulate this in software. So what we did was to come up with some kind of functions, exponential functions, to do this type of distribution. We wrote that into MATLAB first to do simulations, and then into a lens design program. And we produced these 2-dimensional distributions and then the 3-dimensional distributions. And then compare with this is the measured distribution of an arc source, and this is what we simulated. It's not perfect, but it's pretty good. It's pretty good. This is an illumination optics task in optical design. Any question? Well, lens design. to me, has been very, very rewarding in my life. I have a practice. I do teach here the introductory lens design course. I also teach an advanced lens design course. So I have contact with all of you. I love sharing with you what I know, helping you to learn. My job is to helping you transform you from someone who wants to learn lens design to someone who has the skill of lens design, to get the theoretical background necessary, some of the experience through homework, and then experience with the lens design programs. What do you get when you have this skill? Well, you have more opportunities for different jobs because employers love lens designers. There are not so many lens designers, competitive or competent lens designers. There are many, but we need more, even more, okay? What do I get more in addition of helping you learn optical design, lens design? Well, I have a consulting activity. I am asked often to help doing this design, that design, and that is very, very rewarding too. And it helps me to understand what's happening in the industry so that when I am teaching you relevant stuff, the stuff that is happening now. So lens design is really an awesome activity, but I understand you have many interests, and my goal would be to make sure to teach you the skill and so that you can have it and maintain it so that for different jobs you can practice it. And with this, I'm going to stop, and thank you for your attention. Any question? Yes.
So you said glass has a higher index of refraction than the plastic, but has anyone done any research into, I guess, more exotic materials that have even higher indexes of refraction, or are we just sticking with glass?
That's a good question. In lens design Optic 517, one of the things we teach to the students is that a student, an optical engineer, has to be aware of any new material, because usually every design is limited by the material. That's when you know you can do better. And every time there is a new material, everyone says, I want to know about it, because that can represent lots of new patents, okay? New technology. As a matter of fact, DARPA has now the Extreme project program where they are developing these negative index materials or metamaterials with new properties. And there is a lot of interest because new solutions that will lead to what? Less cost, smaller, more power efficiency. So yes, new materials are very exciting because they open new opportunities. Okay, guys. Yes.
Academic research and lens design. I see like a lot of industry integration and contracting and consultation happening in lens design, but is there a lot of, I guess, research into, I don't know, like new design forms or fields like that within lens design?
Yes, there is research, and just let me mention one example. One of my students did his dissertation in a variety of topics about lens design. One of them was, for example, in coming up with a theory on how the irradiance, light irradiance is distributed, how it depends on optical aberrations in a lens system. Another part of his study was on developing this type of surface for cell phone lenses. There are several examples of innovation in lens systems, lens forms. But new lens forms depend on materials. Thank you. Yes?
designing very small lens systems versus very large lens systems? Are they very different areas, or can you apply it very similar?
Well, from the lens design point of view, it's pretty much the same. You use the same tools. But from a practical point of view, it's very different, because once you have a lens that is beyond 2 or 3 inches, the cost will be very high. Very small lenses benefit from the fact that because the material is very small, you can use very exotic materials. And also, cell phone lenses have shown how many physical problems are mitigated by the size. So there are some differences. But from the ray tracing point of view, it's different. You just want to get a good image quality. One thing that helps with the small systems is that the wavelength of light stays the same. Okay, Paul.
PM after lunch as usual. First of all, for any of you who are interested in BEC physics, there's an addition to the lab schedule out there that I just penciled in. It's one of our BEC labs that is available, both in the 1 to 3 and the 6 to 7 time slot. Also, Jennifer Barton is going to offer a guided tour of the
Hello everyone, welcome to Tucson, to those who haven't been here before, and Happy New Year. So yes, as Paul says, my name is Michael Hart. I'm another faculty member at the college here. And my work here emphasizes high-resolution imaging in the face of various attempts by nature to thwart us in imaging with high resolution. So think, if you will, of looking across a hot parking lot during the summer in Tucson in July. Come back, then you'll know what I'm talking about. You see objects on the far side of the parking lot that are apparently shimmering. They're dancing around. Of course, the objects themselves are not warping and distorting. It's the light rays between the object and your eye that are being refracted by changes in the refractive index of air, because refractive index of air is a temperature-dependent quantity. So what if you were to take a long exposure, though, what you would see is images of the things on the other side of the hot parking lot all blurred out. And there are various ways in which we can try to overcome the degrading effects of that dynamic atmospherically induced aberration. Adaptive optics is the one that I'll be talking about here, the one that we primarily focus on in my research group. It has a lot of applications. For example, a nuclear engineer who wants to look through the water jacket around the core of a nuclear reactor to see that there aren't any cracks in the containment vessel. That would be bad. I don't know if Jim Schwiegerling told you a little bit about his research earlier in the day about looking into the human eye and the aberration that can be corrected with these techniques in ophthalmology. Where I will focus my time today is on the use of adaptive optics for astronomy, hence the title of the talk, Taking the Twinkle Out of Starlight, which is where I got my background in this, and where much of the technology is still driven. But before I talk about how we take all the poetry out of starlight, let me tell you a little bit about me, lest you come away from your experience here thinking that we're all a bunch of dry and dusty academics. I assure you we're not. I've been here a couple of years now, and it is the most stimulating academic environment I have been in for perhaps ever. There are a lot of very kooky, very bright people in the college. It's a privilege to be one of them, at least the kooky part. It is a wonderful place I have found in my 2 years here to study, to work, to learn, and to build a research program. So when I'm not being an optics professor. This is a little bit of what I do. I ride horses. Anybody else here a horse person? Oh, great, a couple of people, good. I used to do a fair bit of show jumping in my youth, but I find as one gets older, they make the ground harder, so landing on it is just, so I tend to do less of that now. I fly planes, small ones, and flying them upside down is more fun than right side up. I fly aerobatics up in Chandler. I'm a drummer in a Scottish bagpipe band here, so this is what we do after we win a competition. And okay, I have to admit this is what we do after we lose a competition as well. But and I design and make furniture and do silly things like camp in Death Valley with my wife in the middle of June. But it's a wonderful place there to lie in the back of a pickup truck and watch the stars. They go on forever. It's awesome. And, well, frankly, the less said about that character, I think you'll agree, the better. So moving on to stars, here is a conglomeration of a few 100 billion of them. And, oh, by the way, so I have to tell you, one of the things that got me into astronomy was another collection of a few 100 billion, actually probably about 1 trillion stars. If you go out tonight, right after sunset, and you look up a few degrees to the northwest, between the great square of Pegasus and the W of Cassiopeia, about halfway. If you've got good eyes, I don't, but you guys do because you're young, you'll see M31, the Andromeda Galaxy. And it's a beautiful wintertime object. And it has the distinction of being the furthest object in the universe which you can see with the naked eye. And I used to lie on my back in my parents' back garden when I was about 12 years old with my star charts and my red-shrouded lamp, my binoculars, and I look up at M31. And consider this. It's 2.5 million light years away. And it's on a collision course with us at 250,000 miles an hour. But you don't have to worry yet. It'll be here in about 4 billion years. At which point the night sky will be truly amazing for anybody who's left on the Earth. But think about this as you're looking at M31. The light that started, the light that you're looking at right now as you're thinking this thought, left that galaxy 2.5 million years ago, before the human race even evolved into existence. And for me, that's just mind-boggling. The scale and grandeur of the universe is stunning. And don't ever take that for granted. It's awesome. And we get to study it here as our privilege as scientists. And it's awesome in the true sense of that much-abused word. So anyway, think about that as you're looking at M31. Here's another galaxy, NGC 5972, in 2 pictures. One taken from a fairly sizable 4-meter telescope on the ground, and another from the Hubble Space Telescope. Now, if you were an astronomer or an astrophysicist trying to understand the physics of what is going on in this conglomeration of stars, which one would you choose? Right? Well, that's why we put the Hubble telescope up there all those decades ago. Now, that's one way of getting out of the atmosphere. The atmosphere has this blurring effect seen there in that image of NGC 5972 from the ground-based telescope. And it's clearly obscuring information that if you're an astrophysicist, you would like to get out. By the way, these colors are pretty approximately true. The green here is doubly ionized oxygen in a well-known transition. So there is physics going on here that you would like to explore, which is smeared out by the effect of the atmosphere. Now, getting rid of the atmosphere is, well, perhaps not entirely feasible and maybe not a good idea for other reasons. Going into space certainly works, but it costs about 2 orders of magnitude more to put a telescope of a given size in orbit than it does to operate it from the ground. You just can't go flying 30-meter telescopes, whereas we are building 3 of them on the ground now. And I don't know whether you folks have yet been over to the Mirror Lab or whether that's still to come on the agenda, but you will see pieces of a 25-meter telescope being built there. So that's a reality. Now, of course, lambda over d, right? The angular resolution of an aperture of size d looking at wavelength lambda. That's what you get if you put the telescope in space. If you're operating on the ground, you're limited instead to the resolution of a 10-centimeter telescope by this turbulent dynamic behavior of the atmosphere. So there are two reasons for building, two reasons. Churchill did that to the troops, and he was reminded not to flip them off. So my apologies. Two reasons for building big telescopes. One is obviously a big light bucket. The other is resolution. The big light bucket, okay, you get that. But with resolution, you suffer because of this atmospheric effect. So how can we get around it? So the PSF, the point spread function, always makes things worse. This is the second law of thermodynamics. In fact, if you follow it through, it always degrades the information that you would like to know. And here is an example of the adaptive optics solution. This is a little animated GIF of some observations that we took a few years ago on this telescope. This is a 6.5 meter MNT. This primary mirror was the first mirror at that size made down at the Mirror Lab. Now in operation at this telescope, which is about 40 miles south of here on Mount Hopkins in the Santa Rita Mountains, and where I did most of my PhD work. And this is an image, more or less real time, of a star in T Tauri, it's called. It's the archetype for a class of very early stars. It's only about 1 million years old. It's still forming from the cosmic soup. It's a triple star, at least, and this is the primary component that you see if you look up there with a pair of binoculars. It's too faint to see with the naked eye. But here, in this version, this part of the movie, the atmosphere is just doing whatever it will. So this is a series of short-time exposures where you see speckles, because this is essentially coherent light coming from an unresolved source, dancing around as a result of the atmosphere. Some of that bouncing motion is actually the telescope bouncing in the wind. Another problem with having giant structures that are open to the air. But at this point, you can see that there's one star, and maybe you can catch an occasional glimpse of something down there. Now we turn on the adaptive optics system, and magically, not only is the image much sharper than it was before, we're about at the diffraction limit of, this is 1.6 microns, I think, the astronomical H-band, where these data were recorded. Not only do you get an improvement in resolution, you get an improvement in detectability as well, because you've taken a given amount of energy and squished it into a much smaller area on the detector, so the peak goes up by conservation of energy. And now, not only do you see that there's a source here, there are actually two. That thing that you couldn't see before is now resolved as its own binary star. And it turns out, astrophysically, these two stars together are more than twice as bright and twice as massive as this one here. And in fact, this guy is completely invisible at visible wavelengths. You have to go to the infrared in order to be able to see it at all. So how come this thing is so faint compared to a lower mass, lower brightness companion? The reason is, we suspect, although we don't know for sure, there's a massive edge-on dust disk, and we're staring through the dust this way, and it highly obscures this a pair of stars on the inside. And that's the kind of dust disk out of which planets are formed. So astrophysical information is coming out of here of our use of adaptive optics on this 6.5 meter telescope. So AO, I'm going to be focusing, as I said, on astronomical uses of it. There are other applications of adaptive optics. A few of them are listed here besides astronomy. Microscopy, retinopathy. Here's a wonderful little movie that I stole from Jim of images of a human retina taken in vivo with and without adaptive correction. So there's without, you turn on the AO system and suddenly you can see the rods and cones and shadows of blood vessels beginning to appear here. The whole thing is dancing around because that's what we do, right? So you can detect the predator in the bushes over there. We cannot hold our eyes still. It's physically impossible to do that. Lots of other applications of AO. Can be mounted on planes looking downward. It's used in laser communications, X-ray beam lines, and so on. But as with a number of technologies like detectors, astronomy drives much of the technology development in adaptive optics, hence my focus. Now, here's another example of AO in action for a slightly non-astronomical use, although it's still a large ground-based telescope. The Air Force runs this big 3.6 meter telescope, well, fairly modestly sized these days, on Haleakala in Hawaii, which is where I'm lucky enough to go and spend a fair amount of my time. And in fact, one of my PhD students has spent 2 summers working at that site. So yes, come to the college, and you get to go to cool places like Maui for your internships. She had a choice, Maui, Albuquerque. Well, let's see, that took about 3 nanoseconds. So here is, again, more or less real time in this movie, images of this telescope taking pictures of that telescope. And you will recognize, of course, HST, the Hubble Space Telescope, as it flew over the site, with and without the adaptive optics system on this guy turned on. So a little bit of history. Adaptive optics was invented by an astronomer, Horace Babcock, at the Mount Wilson Observatory in Southern California, 1953. The technology was just a little not there in the 50s, although he, being the genius he was, actually built something out of analog bits and pieces and made this first AO system work. But it wasn't until 20 years later that AO systems really began to be built for use on large telescopes. And it was only the US Air Force that had both the money and the interest to fund what essentially that was the limiting step at that time, which was the computation. And of course, they weren't interested in looking at things astronomical. They were interested in looking at Sputniks and so on. But hey, that's what led them to make the development. So most of you are too young to know what computation was like in the 1970s. But imagine your favorite cartoon steam train wheezing and puffing and heaving and groaning and doing its mighty best, and you'll get some sense of what computation in the 1970s was like. So back then, they built literally a room full of computers that had a fraction of the computational power of this, Spectre and Meltdown notwithstanding. It was enough then to run AO systems that could produce images sort of approximating this. Back in another 20 years past, 1990s, astronomers took over again. There was a grand release of what was then classified information from the Air Force because they saw the astronomers catching up and they didn't want to get left behind, and they didn't want to lose the credit for what they had already done but weren't allowed to talk about. So that was actually, I was at the meeting where they did that, and it was a huge benefit to both communities. We were finally able to talk to each other, and we've been doing that ever since. All right, so let me tell you a little bit about the physics that leads to the aberration, which leads to the need for AO, and gives people like me jobs and careers. And people like, I should mention, yes, Jose mentioned his little company. Well, yeah, we all have little companies that we run. And the company I run has been hiring lately because there is industry and government interest in adaptive optics. It is a hot topic. We've doubled in size over the last year. So there are jobs available in this business. But here's turbulence in action. It's turbulence in the atmosphere which leads to this mixing of refractive index, air of different temperatures, via something called the Kelvin-Helmholtz instability. And you see it in this cloud right here, little waves. And these are, honest-to-goodness waves, just like on the ocean, between shearing layers of atmosphere at different temperature. And one of them down here happens to be warmer, because it's lower, and moist enough that moisture is condensing so you can see the waves in the clouds. And here's a little video of the same thing happening right here off a peak in the Santa Catalina Mountains north of here. I was up there with a buddy of mine at a 61-inch telescope, which you can see. It's a nice clear day. If you go up to the 8th floor of this building and look to the north, you'll be able to see this telescope we were at. And you can see the waves here forming. Oh yeah, there's a nice rainbow here that I picked out. And here's my buddy Stuart. This is what astronomers look like after 3 or 4 days at the telescope. It's a little ratty. But we have this layer of colder air coming up, being blown up this way over the peak of the mountain, and the layer of this is warmer air coming up here, colder air down there where the water condenses, and in this shear layer you can see these waves developing. So that's what leads to the turbulence and the refractive index mixing. So here's what happens to light as it passes through the atmosphere. Let's imagine we had some objects in the sky that we're interested in looking at. waves of light with nice, pristine, flat, collimated wavefronts come towards us. And if they're coming from M31, they spend 2.5 million years galloping through intergalactic space at 3 times 10 to the 8 meters per second. And then 300 microseconds before it reaches your eye or your telescope, it goes through this aberrating atmosphere and gets all messed up. And the astronomer's like, no! Oh, put your telescope in space. But it's this last 300 microseconds that causes all the grief. And these pristine flat wavefronts end up becoming aberrated, distorted. And they form images as seen through your telescope here, idealized as a single positive lens. And you get an image of the scene, which is now blurred. Right? So how could you fix this? If you had a means of flattening those wavefronts out so they look like this, you'd be golden. Right? You'd now restore the imaging that the telescope would have were it in space. And that's the goal. So how do you do that? Well, if you put in a mirror, a deformable mirror, whose shape can be changed in real time in response to the shapes of these aberrations, you could potentially do that. All right. How do you know what shape to make the mirror? Therein lies the trick. And here is the system to do it. Those of you who will be sticking around for Monday and are going to see the lab, the AO lab up on the 6th floor, will actually see a system doing this. So here's how it works. Undistorted wavefronts come in. Distorted wavefronts come out of the bottom of the atmosphere into the telescope. Let's trace the path of the information. Here, first of all, encoded as light. Here's a beam splitter. Some of the light goes through to our science instrument. This is our camera, our spectrograph, our polarimeter, our whatever it is. This is doing our astronomical science. But we separate off a fraction of the light, and we send it to another camera. And in this case, it's just, we'll call it, think of it as a black box for now. Don't ever trust anyone who says, take my word for it, right? Because it's generally not true. But for now, we'll just think of this as a magic box that detects the shape of the wavefronts. That camera is read out to the ubiquitous computer. You can't build an optical system these days without a computer. And the computer figures out, on the basis of the signals measured from this detector, how to change the shape of a rubber mirror. It's not literally rubber, it's made of glass or some other material, but it's a mirror whose shape can be changed in real time. Such that when this deformed wavefront bounces off it, it comes off flat. So we put on the conjugate aberration, equal and opposite. Actually, equal divided by 2 because we get a factor of 2 because we're in reflection. All right. So what we're doing then is we're making a measurement, making a correction, making another measurement to see how well we did, making another correction. In other words, information is flowing round and round this loop. Half of the time it's encoded as photons, half the time it's encoded as electrons, electrical signals. And because the atmosphere is dynamic, you can't just make a measurement, make a correction, you're done. Images are good. No, the atmosphere changes. So you have to continually make measurements, make corrections. It turns out you need to go at about 1,000 times a second. That's just what nature tells you about how the atmosphere how fast the atmosphere evolves. So we're doing this, we're making measurements, making corrections at about 1 kilohertz, and changing the shape of our mirror 1,000 times a second. And basically what this detector is doing is it's looking at some beacon in the sky, and we'll talk about that in a minute. What does that look like? It's looking at what the beacon, about this source of light, actually looks like, and the computer is then comparing what it sees to what it knows the shape of the beacon should look like, and then figuring out how to bend the mirror in order to turn the one into the other. So, large telescopes need adaptive optics. The bigger the telescope, the more it needs AO. And this is sort of why. We can think about the angular size of a resolution element. The trouble with the atmosphere is it blurs our images. It degrades the resolving power of the optical system. Okay. If we took the atmosphere away, here's the diffraction limit. This is the angular resolving power, or angular resolution of the telescope, where these two quantities, one is just, the lambda is just the wavelength you're looking at. D depends only on the telescope. If we put the atmosphere in place now, suddenly the angular resolution becomes lambda over this quantity called R0. And if you ever get into adaptive optics, you will see this everywhere throughout the literature. It's a length parameter that quantifies the aberration that you encounter in the atmosphere, and it depends only on the atmosphere. What does this suggest? So this implies The angular resolution of the telescope depends on the wavelength that you're looking at and an atmospheric parameter. It does not depend on the size of the telescope. You can make the telescope as big as you like, and it doesn't help. Take the ratio of these, and you find then that the improvement you can get by using adaptive optics scales as the diameter. So the bigger the telescope, the more it helps. Here's one of the telescopes that we use and operate at Arizona on Mount Graham. A couple of hours drive east of here, close to the New Mexico border. 2 8.4-meter diameter telescopes on a common mount configured as a co-phased interferometer. Both those mirrors made down here, of course, at the Mirror Lab. And if we put adaptive optics on this, which we have done several different times for different instruments, it improves the resolving power by at least a factor of 20, depending on the wavelength you're looking at. Amateur astronomers can breathe a sigh of relief. If you go out and buy one of these, you don't need to then spend $1 million buying an adaptive optics system because it won't do you any good. So you needn't worry. So I mentioned that an AO system needs a beacon of light in the sky to look at in order to do the analysis of what has happened to that light as it traverses the turbulent medium. And what astronomers like to do if they can is use a natural star. But you need you have to have a star of a certain brightness, typically magnitude 11 or 12, for those who think in astronomical magnitude scales. It turns out that there aren't that many of them. So if you want to look at a galaxy in a very sparsely populated part of the sky, ain't no stars there, won't work. But you can make your own. And here's one way to do it. You shoot a laser up here. This is my favorite 6.5-meter MMT again with a green laser. 532 double YAG. It's actually exactly the same color as my pointer laser here, same technology. And make a beacon of light in the sky. You can do the same at LBT. Here's 2 halves of the LBT with lasers coming out of them in a nice time-lapse video. This is the moon, by the way, as we approach dawn. And you can see the lasers shooting up. Each one of these is, in fact, a constellation of 3, but they're close enough together that you can't resolve them in the picture. So there are actually 6 laser guide beacons being sent up from the LBT here. Yeah? In this case, each one of those is 18 watts. So we've got about 50 watts of light coming out of each aperture, which means we have to worry an awful lot about planes and satellites. So if you go, being a pilot, I go look at NOTAMs all the time, notices to airmen, and it will say, don't fly around this observatory because you're not going to blind anybody, but you will startle them, and that's not good when you're a pilot. You don't want surprises. There was another question?
I was wondering why they use multiple guide stars for each telescope. Is it to probe different layers of the atmosphere, or?
Come to my class. The short answer is yes. So the reason for using multiple beacons on this, and in fact on the previous slide where there were 5, or you couldn't see, is to correct over a wider field of view than you can if you use only one, because you're sampling along different lines of sight. You can actually use a tomographic algorithm, the same way you can isolate something in the human body by taking radiographs from different perspectives. You can sort of isolate different lines of sight, and where those lines of sight intersect is where the tumor is in my body. Right? And you can do the same thing with the phase objects which constitute the atmosphere and figure out where those important layers of atmospheric aberration arise in range. I should have said, feel free to interrupt, ask questions, because I'll go on about this all day if you let me. It's one of my favorite topics. So do interrupt. So yes, we need a beacon. And here's an example of another beautiful movie made now a couple of years ago, almost 3 years ago, by one of my colleagues across the street at Stewart Observatory using that telescope. So this, in the background here, is the constellation, the moon, Io, moon of Jupiter, which, as you probably know, is volcanically active. It has sulfur volcanoes erupting on it, which is what you see, the bright spots here. This is obviously artificial color. But notice the pattern here. You'll see these fringes. Each one, well, this guy here, Pele, is an unresolved sulfur volcano. It's unresolved by the LBT, so what you see is this 3-fringe pattern, the point spread function of a 2-aperture interferometer with large apertures. So those are Young's fringes. that you see. And they're nice and stable because the AO system is running. If you turn the AO system off, the entire image here would be blurred out with a resolution about equal to the size of IO itself. It would be a single unresolved blob. You'll see there's a distinction between Loki. Loki is actually slightly resolved, so those fringes are a little bit blurred. So it's not as sharp as Pele. And, of course, there's the elephant in the room that I haven't mentioned yet, this guy marching in front. Phil Hintz, my colleague, was lucky enough to capture Io as it was being eclipsed by another moon, Europa. Just happened by good fortune, I guess. And it made an awesome movie. But you might, I don't know how aware you are of the makeup of the moons, but Europa is an ice moon. In fact, there's some thought that maybe under the ice surface there is liquid water, and maybe that's an environment in which life can form, and there are missions planned to go find out. So why does an ice moon appear black? It's obviously the sun is here, because otherwise we wouldn't see Io. So we have a fully illuminated ice body which looks black. Here's a hint. Ice may be bright in the visible, but water has some very, very wicked absorption lines in the infrared. So at 4.8 microns, ice is black. And that's why Europa appears dark. So this is another example of local astronomy, solar system astronomy, where adaptive optics is allowing us to probe the astrophysics of what's going on with the volcanology of Io. All right, so we've talked. Oh, yes.
When you're looking at different wavelengths, do you change the frequency of your guide stars?
No. So let me back up here. In fact, hello. Yeah, there we go. So this guy here, the beam splitter, is generally a dichroic. So I send the visible wavelengths from the beacon over here, and the infrared wavelengths go through. And fortunately enough, the atmosphere is sufficiently achromatic that if I make a measurement in the visible and apply a correction on that basis, it will be good in the infrared as well. Going the other way is slightly problematic, but if you go from short wavelengths to long wavelengths, you're generally in good shape. All right. So we've talked about the beacon and how you make your own. The next thing is the wavefront sensor, this magic box that somehow tells you what the shape of the aberration is. If you're into radar or radio astronomy, you can, as well as detecting the amplitude of the electric field, you can also directly detect its phase. Right? I mean, radios in your car do that all the time, and I only wish we could do that in the optical. But we can't, for reasons that I won't go into here, but come to my course and we'll learn all about it. I can't measure OPD directly at each point in the telescope pupil. I have to come up with some indirect means of doing it. This is the usual way. It's by no means the only way. In fact, it's not the way that the LBT uses, but it's ubiquitous, almost ubiquitous in systems around the world. The so-called the Shack-Hartman sensor, originating from a Hartman test by a professor at Potsdam 100-odd years ago to measure a crappy telescope lens that Kaiser Wilhelm had just commissioned to great fanfare, and then they found out it was a terrible telescope, so they had to go refigure the lens, and Hartman figured out a way to test it, because you can't fix what you haven't measured. Beat on that with all my students. Phil over there will confirm that. He's one of my students there. And then modified by Roland Schack, who was a faculty member here. And the way so what happens, you put a series of lenses, small lenses, lenslets, in the pupil plane of the system. And if a flat wavefront impinges on those lenslets, back here in the focal plane, you get a series of spots, little unresolved images of the source out there, seen by each one of these lenslets. Now, if you put an aberration onto the wavefront, the local wavefront slope over each lenslet causes its little image to move. So if I look at my scrambled pattern of spots, the position of each one of those spots tells me directly the mean wavefront tilt over the corresponding lenslet. So I'm measuring the first spatial derivative of the OPD. It's not the quantity I want, but it's something pretty darn closely related to it. And I measure d phi by dx and d phi by dy, do a simple spatial integration, and I can come up with an estimate of that wavefront shape. Once I have that, I can put that on my deformable mirror by pushing my actuators appropriately. So you can begin to see how this works. How you can make a measurement, you can do a computation, you can apply a correction to a deformable mirror. So that's the measurement piece. Then there's the so-called reconstructor piece. This is the part in the computer. And yeah, we're taking wavefront sensor signals, intensities measured on a bunch of pixels, and we're turning those into drive signals. And yeah. Oh, shut up. Phone calls are annoying sometimes. My apologies. Yeah, we won't spend a semester on that, but suffice it to say for now that there is a linear operation. So what we're doing essentially is a spatial integration of these slope measurements. An integration is a linear operator. Right? So I can couch it as a multiplication of a matrix times a vector. So here is my vector of measurements that I've made. I just simply arrange them lexicographically into a column vector. Then I multiply them by some well-chosen matrix, and out comes another vector which tells me how to push all of the actuators on my deformable mirror. Now, the trick is to know what the elements of that matrix should be. That's the calibration piece, which we could spend a semester on, and some of you, and those of you who are going to the lab, will actually be doing that calibration. But there's a well understood procedure for calibrating this reconstructor matrix, and thereby turning my wavefront measurements into deformable mirror commands. All right, so here's the next piece in the chain. Once we have deformable mirror commands, we can apply them to the actuators of my rubber mirror. And there are many technologies for making deformable mirrors. Here's a couple of them. So this is one. It's a MEMS micro-electromechanical system. It's fabricated in a growth chamber with a layer of silicon nitride on top, which can be deformed. In fact, this is an example where each one of these little hexagonal segments has 3 actuators on the back, so it can be pushed up and down in piston, and it can be tipped and it can be tilted by little electrostatic actuators that are buried behind it. So the whole thing is only 3.5 millimeters across, and it has something like 110 degrees of freedom that you can use to take out aberration. Here's another example. This is the kind of technology that's been around for 40 years. This is a mirror that's actually in use at one of the 2 Keck telescopes on Mauna Kea on the big island of Hawaii. And here you see the Keck logo reflected. This is the front surface. So this mirror is about 6 inches in diameter. On the back of it are 349 stacked piezo electrodes. So you apply 1,000 volts to each one of these, and you make the crystal grow or shrink appropriately according to the sign of the voltage. And the tip of each one of these 349 actuators is glued, literally, to the back of this glass face sheet. So as you push the actuator and pull it, you're driving the local surface of the deformable mirror in OPD. There are many other technologies for making deformable mirrors as well, and this is the one that we're particularly proud of here. Deformable secondary mirrors. So again, my favorite MMT 6.5 meter telescope on Mount Hopkins down there, with an adaptive mirror that is included as the secondary mirror of the telescope itself. This is an absolutely terrifying piece of glass. It's 60 centimeters in diameter, and it is less than 2 millimeters thick, and it's glass. So it's a giant contact lens, and it takes 2 years and $2 million to make one. So it's like, oh my. And not only is it just any old thin piece of glass, it's optically figured to high precision, to about 10 nanometers RMS surface as an ellipsoid. So there's a lot of expertise, time, money, you name it, that went into making that. And on the back of it, it has 336 actuators. They're actually little voice coils, so little magnets, permanent magnets glued to the back of this guy, and coils that through which you can pass a current. And so the current, the field, the magnetic field that you induce by passing a current through the coil interacts with the permanent magnet and pushes and pulls just like a loudspeaker. I've often wondered what would happen if you tried playing Ode to Joy through this, or We Will Rock You. That's a little scary. I hate to break it. But this is the first time we installed it on the telescope. This is me and a couple of my colleagues on the man lift with the telescope pointed at horizon, so we can actually get access to the secondary mirror hub for installation. Behind it is what used to be a supercomputer back in the day when you could build supercomputers out of integer processors. This is C40 DSPs from Texas Instruments. Yeah.
Just like a subtle question, you guys don't have to wear like clean suits when you're working with such like a precise mirror or something like that?
Well, think about it. We operate this telescope in the open, so it has got to be able to survive environmental conditions. And in fact, you bring up a very, very sore point. One of the aspects of this mirror, and it's actually highlighted here, this is one of the two mirrors that's on the LBT right now on the twin binocular telescope. This is the thin face sheet, now 90 centimeters across and 1.7 millimeters thick, so even more terrifying, with now 672 permanent magnets glued to the back, and this is the mating piece. These two pieces come together. We sense position with little capacitive sensors that span this gap, which is about 80 microns. That gap is open to the air. Any dust that gets in there ruins the mirror. Well, it ruins its operation. And we had the great misfortune, right after we installed this, to have a volcano go off in Indonesia. And it put so much dust into the air. And we learned the hard way that, environmental conditions really can affect the performance of this, and we had to scramble and mitigate and figured out ways to do it. But this was quite the engineering triumph, because we had people, well-respected engineers at the time, telling us that our control mechanism for this mirror would not work, and they were telling us why it would not work. And being dumb, naive astronomers, we went ahead and built it anyway and made it work. So, here's the anatomy of one of these things. So this is the business part. In fact, the reflective side is on the bottom. The LBT, for those who, you'll recognize this is a convex surface. The reflective surface here is concave. The LBT is a Gregorian design, as a concave secondary mirror, unlike most astronomical telescopes. But those two pieces are here in this photograph of the stack up. Here are all the actuators, the tops of them. There's an aluminum plate here which gets rid of the waste heat. There's another supercomputer in here which maintains the actuator positions where we want them. And there's a big hexapod there which allows rigid body motion of the whole thing to collimate the telescope. And there's two of those in operation on the LBT. Let's see, got a couple minutes. So here's one of the cool astronomical results that comes out of, in fact, that telescope, the LBT. Again, from a couple of years ago, Steph Salem, who was a PhD student over at Optical Sciences, got a paper in Nature while she was still a student. So you can do really cool stuff while you're here and do things like become first author on a Nature paper. But she was looking at a star with a planet-forming disk around it with the terribly poetic name of LKCA15. LK stands for Lick, the Lick Observatory on Mount Hamilton in California. But she was looking at these guys. So the flux that you see out here is actually millimeter wave flux measured at the VLA, the Very Large Array outside Socorro, New Mexico. And the observations that she was making were of two planets, B and C. There's also a suggestion of another one here, D. I'm not sure if that's real or not. But for the first time, she was able to show conclusively that this guy is formed by accretion. There have been two conflicting models of how planets form in these circumstellar disks. And she was able to distinguish between them by showing unequivocally that this planet is being formed by accretion of hot material onto it. The telltale is this blue light. It's not actually blue in real life. It's red. It's 656 nanometers. It's the H-alpha line. It's the line that monatomic hydrogen forms as the electron drops from n equals 3 to n equals 2, the Balmer series. And that only happens when hydrogen is at a temperature of about 10,000 Kelvin. So this is and it's a very unique signature. That's the line. It's hydrogen, by golly. So this is hydrogen falling onto the surface of a planet and being heated as it does so. So hence, because she was able to make such a powerful measurement and distinguish between these two hypotheses, that's what got her into Nature. And it was because of the resolving power of the AO systems that she used on 2 different telescopes, in fact, both of which we built here, that she was able to separate out the light from the planet itself from the light from the star, which is right there, and orders of magnitude brighter. You have to be able to separate these two in angle space in order to be able to block out the very bright star and prevent the signal from the planet from being totally swamped by photon noise from the star, scattering into the region where you want to see the planet. So AO and its resolving power enabled this observation. Here's another one that I just think is super cool. A series of observations made by my colleague Andrea Ghez at UCLA. She's built a career looking at this. This is highly processed real data taken over a period of a couple of decades of the region around the center of the Milky Way. And you might know that, in part, thanks to Andrea's work, we now know that there is a black hole at the center of our galaxy with a mass of about 4 million times the mass of the Sun. And it's a very dense region with a whole lot of stars in orbit around the black hole. And in particular, there's this one here, SO2, which has, by now, completed more than one orbit in the time that it has been observed. So we expect from general relativity to be able to predict with high precision what each of these orbits will look like. And we know them in 3 dimensions. We can see the 2D projections here, and we also know their radial velocities from the spectroscopic measurements. So we know the 3D orbit of each of these stars. GR, general relativity, allows us to predict what those orbits will be to high precision. Wouldn't it be freaking awesome if these stars didn't do that? Quantum mechanics and general relativity, they don't get along. One of them has to break at some point, right? My bet is that general relativity will break before quantum mechanics does, but somehow there has to be some experimental evidence that general relativity isn't working. We haven't got that yet, but here's one laboratory, if you will, which might allow that measurement to be made. And again, it's enabled by adaptive optics by the ability to resolve these individual stars in their orbits at extreme distance around this 4 million solar mass black hole. So I'm going to wrap up now, and we can all go take pictures and then get to lunch. Right? So the crucial thing about adaptive optics is that it applies corrections to the light before you detect it. And from a quantum mechanical perspective, that's essential. Once you collapse the wave function of the photon, there's nothing you can do about the built-in shot noise, the fundamental photon noise. If you do the correction before you detect it, you've made things fundamentally, in some sense, better from a signal-to-noise perspective. And now AO, I had an argument with the builder of the Keck telescope about this once, at a time when adaptive optics was not on all the big telescopes in the world. And I said, I predict it will be. And he said, nah. Well, and he won a Kavli Prize, so I'm waiting for mine. But now it's almost true now. There are no big telescopes in the world that don't have adaptive optics on them because they are very expensive instruments to build. We have to convince taxpayers to spend the money somehow, and that's through doing cool science. And so for the telescopes you want to build, you want to get the maximum science out of them possible. So here's the next one, folks. You will have seen or are about to see parts of that. This is the Giant Magellan Telescope, of which the University of Arizona is a full partner. Those 8.4-meter mirrors are being built at the Mirror Lab now. It's going down on a peak in the Andes. It's being built now. First light is predicted for 2023. So this telescope will be up and running on the time scale when you all will be starting out your careers, maybe cementing your careers. You'll have an opportunity, if you wish, to work on this, to use the results from it, to figure out how to make it better. Come to Arizona. Thank you all. Let's go to lunch.